Hello everyone, my name is Yoon Chae. I'm a PhD candidate at George Mason University. Today I'm going to introduce our work, high-speed mmWave Wi-Fi backscatter using commercial Wi-Fi device. This is a joint work with KAIST. Recently, in the field of wireless networks and mobile systems, there are two strong trends. One strong trend focuses on achieving high-speed communication such as 5G, 6G, and mmWave Wi-Fi, and so on. However, these systems require high power consumption. On the other hand, another strong trend emphasizes low-power wireless communication. Although they can operate with small power, they cannot achieve high data rate. Since they are targeting totally different goals, having a high-speed wireless communication with low power consumption is a fundamentally difficult problem to achieve. In near future, there will be many high-speed IoT applications. For example, your IoT device wants to transfer high-definition video streaming to play holograms between your IoT and AR/VR devices. To support these high-speed applications, we need to have high-speed IoT communication while maintaining low power consumption. In this paper, we address this challenge by employing the mmWave backscatter technique. We leverage the large bandwidth of mmWave to enable a high data rate. Furthermore, since our backscatter system uses a passive device, we ensure ultra low power consumption. In mmWave backscatter system, we have two entities, the reader and the tag. The transmitter transmits a mmWave signal, and a tag radiates a modulated signal. mmWave backscatter has been studied in some prior works. However, these systems use dedicated devices or hardware, such as SDR or FMCW radar, as a backscatter reader. Therefore, the need for the dedicated device limits the adaptability. In this paper, we ask the following question. Can we utilize existing networks for mmWave backscatter? Our mmComb is the first high-speed mmWave Wi-Fi backscatter system using commercial Wi-Fi device. Since existing mmWave Wi-Fi devices are used as a reader, it improves adaptability and ease of integration. Let me briefly explain how mmWave network operates. mmWave Wi-Fi networks uses directional antennas because of large path loss of high frequency. The transmitter performs a beamforming process to find the right direction for communication. So it sends out the beamforming frames with different beams and selects the beam that offers the highest SNR. For another client, it may select a different beam for communication. In our paper, what we want to do here is to seamlessly integrate our backscatter into existing Wi-Fi network and make them part of it. The transmitter sends out a beamforming frame as usual. Here, a tag embeds our backscatter bits inside the beamforming frame and re-radiates it. The receiver creates a new receiver beam pattern to focus on the backscatter signal. Now let me explain how the tag embeds the backscatter bit within the beamforming frame. Wi-Fi transmitter transmits Wi-Fi beamforming frames. The tag re-radiates a modulated beamforming frame. This modulation allows the Wi-Fi bits to be flipped or not flipped within the frame. Importantly, the modulated backscattered frame is still a protocol-compliant Wi-Fi frame with only some bits changed. The receiver can extract the tag bit by comparing the received bits with the originally transmitted bits. By doing so, our system can be compatible with commercial Wi-Fi devices. Therefore, we don't need any hardware or protocol modification. mmComb enables 55 Mbps high-speed IoT communication with low power consumption that consumes less than 100 microwatt. Then the question is, how the tag flip the Wi-Fi bits? The beamforming frames use DBPSK modulation. In this situation, our tag can introduce either 0 or pi phase shift. When the tag introduces an additional phase shift, it effectively flips the Wi-Fi bit. To extract the tag bits, the receiver performs an XOR operation. At this time, in order to extract the tag bits, we need to know the originally transmitted bits. So here we leverage an important observation that beamforming frame structure and payload do not change over time. Hence, even without receiving the original transmitted frame, the receiver already knows the original Wi-Fi bits. Through this process, the receiver successfully demodulates the tag bits. However, there are 4 challenges when we actually integrate this into a Wi-Fi network. Here are 4 challenges: self-interference, identifying the backscatter path, beamforming frame detection, and ensuring unaffected beamforming process. I will discuss them one by one. The first challenge is self-interference. When we consider only the backscatter path, the receiver can effectively demodulate the backscatter frame. However, in the real world, we have multipaths between the transmitter and receiver. Since the original Wi-Fi frame is different from the modulated backscatter frame, the original Wi-Fi signal becomes a strong interference to the weak backscatter signal. To overcome this challenge, there are 2 existing approaches to address this self-interference. The first approach is shifting the center frequency of the backscatter signal to another Wi-Fi channel. This can isolate the backscatter signal in frequency domain from the original Wi-Fi signal. However, due to the large bandwidth, shifting the center frequency in mmWave Wi-Fi consumes too much power. This is not suitable for our low-power device. The second approach is using different polarization for backscatter communication only. However, this requires hardware modification, so we propose a different approach. We leverage the specific property of mmWave Wi-Fi device, which use beamforming to separate the self-interference and backscatter signals in spatial domain. The Wi-Fi receiver has a default receiver beam pattern, which may receive both self-interference and the backscatter signal. To mitigate the self-interference, our receiver generates a new receive beam pattern that eliminates the self-interference direction while maintaining a high gain toward the backscatter direction. Let me explain how we can create this new receiver beam pattern. Each antenna element can be controlled by a wave vector. By controlling these wave vectors, we can create a new receive beam. Our goal is to find a wave vector that constructively combines the backscatter signal while destructively combining the self-interference signal. How do we find this wave vector? Let's say we have a received signal Y, which has both a backscatter signal or self-interference signal multiplied by a wave vector. We define YB as the ideal signal where we only have a backscatter signal. What we want to do here is applying this wave vector to make the received signal as similar as possible to the ideal signal. Let's say the error represents the difference between the received signal and the ideal signal. By finding the minimum differentiation of mean square error, we can find the optimal wave vector. To calculate the wave vector, we need to calculate the autocorrelation and cross-correlation metrics. The correlation metrics computation assumes that the incoming signals of backscatter and self-interference are mutually not correlated. So we adapt spatial smoothing techniques to decorrelate to the two signals. Due to the time limitation, I cannot discuss the entire solution here, but please refer to the paper for more details. This wave vector effectively removes the signals coming in the direction of self-interference and creates a high gain beam in the direction of backscatter signal. To calculate the correlation matrix, we need to know the angle of arrival in each direction. How can we find the angle of arrival? To determine the angle of arrival, we leverage the power delay profile. The power delay profiles gives the intensity of received signal through a multipath channel as a function of time delay. By observing the intensity of each peak in power delay profile and the corresponding gain in different direction for beam pattern, we can find the AOA of different paths. However, we still need to find which path corresponds to the backscatter path to create a high gain beam pattern towards that direction. Interestingly, we observed that our tag operation only affects the backscatter path on the power delay profile. By observing the channel change, we can identify the backscatter path and create our new receiver beam pattern for that direction. I will explain how this process can be integrated into existing Wi-Fi network. In the millimeter wave network, there are frequent beamforming processes to maintain directional communication. We utilize this opportunity. During the first beamforming, our tag continues to be set to state 1. The receiver can find all path directions from the power delay profile as I explained before. In the second beamforming process, the tag is switched to state 0. By monitoring the channel change, we can identify the backscatter direction. With this given information, we can generate a new receiver beam pattern and perform the tag modulation for high-speed backscatter communication. Since our tag utilizes beamforming frames, our tag is supposed to detect only the beamforming frame. Without power-hungry demodulation process, how our tag can detect only beamforming frames? We employ a power detector that converts the received RF signal into voltage information. Even though they are not IQ samples, we found that the control frame and data frame captured by the power detector shows totally different pattern due to the two aspects of the control frame, long preamble and spreading factor. Using this aspect, mmComb tag can only respond to the control frames. Furthermore, our design does not affect the current beamforming process. When AP performs beamforming for station 1, beamforming frame also can be used for backscattering to station 2, and vice versa. Therefore, this way provides a lot of opportunity for backscatter to send the data. We implement the design using the tag prototype, and this tag can support high-speed modulation. For Wi-Fi, there are two types of receivers. One is commercial millimeter wave Wi-Fi receiver. Using this, we confirm that our design can be compatible with the existing Wi-Fi network. Since this Wi-Fi receiver does not provide BER information directly, we connect the IF bridge board received from UCSD group to capture IQ samples just for evaluation. We first performed a micro-benchmark evaluation across various distances and angles. For distance evaluation, we fixed the distance between either the transmitter or receiver from the tag. When we increase the distance of the other component, our tag can provide a data rate of over 50 Mbps up to 7 meter while maintaining a low BER. For angle evaluation, our tag is placed at different locations. It shows that our tag can cover around 90 degrees with low BER. For practical scenario, we place the tag at different positions, including both line of sight and non-line of sight conditions. In the case of non-line of sight, the BER increased slightly due to the SNR drop at the tag side, but still our backscatter system demonstrates robust operation across diverse environments. We further conducted a multi-tag evaluation. Our 7 tags are placed at different locations and they are operating simultaneously. We observed that our tag operation is not interfered with by other concurrent operations. This is mainly because of this. If the transmitter has this kind of beam pattern, 2 tags can concurrently operate. Due to the sparse nature of mmWave channel, only a few out of all tags respond in each transmitter beams. Additionally, due to the receiver beam forming, our system can selectively focus on specific tag of interest. To sum up, we introduced the high-speed mmWave Wi-Fi backscatter system using Commodity Wi-Fi device by integrating our system into the mmWave network. We can achieve high data rate of backscatter communication and maintain very low power consumption. Thank you for listening, and I'm happy to take any questions.